Okay, so I'm gonna, sorry. I'm going to talk about hardness results for structure, for multi-commodity flow problems and other structured problems. And this is joint work with Peng Zhang, who just started at Rutgers, and Ming Ding, who is my PhD student. And this is like really not kind of fancy math we're going to do at all. It's like, it's more kind of about a realization that like the kind of the dumbest and also most amazing tool that we have in theoretical computer science is NP completeness, right? It's the most amazing because it just kind of gives an incredible array of answers, all these problems we know are NP complete. And it's the dumbest because it's so easy, right? Like once you know kind of the general idea, it's often very straightforward to prove an NP completeness reduction. And then we just kind of realized at some point that that actually fast algorithms have sort of progressed a lot. So there's a lot of things where we have like max flow, we now have like super fast algorithms for example. And then we started to get kind of super fast algorithms for a bunch of other problems, like things like computing the stable distribution of a random walk we can do in nearly linear time. Okay, so once you start to be able to do all these things, you want to know, like, are there some of these things on my list of like the next thing I should make a super fast algorithm for that I just can't do, right? And so then we started to realize that some static. Okay, nothing we can do apparently. I apologize. So then we started to realize that that actually you can sort of do kind of a similar schema in the lands of linear programs. And also linear equations. And so once we started to have kind of really great fast algorithms for solving certain kinds of structured linear equations, it became very interesting to prove that that there are other structured linear equations that you're probably not going to get fast algorithms for. And then the place we started for that was here, so linear equations. And this was joined with Peng in 2017. We showed that a bunch of linear equations, so including something that I'll call two commodity Laplacians, that these are able to efficiently encode general linear equations. So if you had a fast solver for them, then you would get a fast solver for all linear equations. So that's kind of a completeness result for linear equations, because in particular, this is a family of linear equations. But if you can solve it, then you can solve all linear equations quickly. And then it was pointed out to us that actually, so what I'll address this much more as I go into the slides, but what I mean is I'll take a linear equation, a general linear equation, AX equals B, and then I will produce a two commodity Laplacian equation, LY equals C, with NNZ of L equals O tilde NNZ of A. There's some asterisks here that I'll explain in a second, but that's the basic idea, okay? So that if I have few non-zeros in this one, I'll have few non-zeros in this one. And so if I have a fast linear equation solver for Laplacians in terms of non-zeros, I'll get a fast linear equation solver for general linear equations in terms of non-zeros. And this holds for any running time that you then would apply as a function of the number of non-zeros now. And so I would suggest that you should think of this as these things are sparse linear equation complete. Right, if your problem is sparse, these are as hard to solve as general sparse linear equations. Okay, general sound issues, I'm sorry. Okay, and now it turns out that, the two commodity Laplacians, these linear equations we really studied because we wanted to show that it's hard to solve two commodity flow, right? So where I mean the linear program. And then it turns out that a good notion of should it be hard to solve linear two commodity flow is that if I have a general linear program, say I want to do, max c dot x, ax equals b, and x is non-negative, that's a general linear program. If now I can encode that as a two commodity flow problem with similar number of non-zero entries, then I have shown, at least in some sense, that two commodity flow is as hard as general linear programming. And so that's what this is about. And now I probably should not have said as much without starting the slides, because they will repeat a little bit, but we have some details here that are important. So when I say a linear program, I mean maximize or minimize c dot x subject to ax equals b, x is greater than or equal to 0, and I only have polylog bits per entry. So that's important. Okay, so that means I can have like polynomially large numbers, but not exponentially large. No, it's fine, it's fine. Yeah. Okay. Yeah, okay, let's maybe not. Okay. We're sorry, we're being told the other mic is just as bad, I think. Okay, sorry. Oh. So I'll try to stand very still. So, okay, so we assume. Okay. Yeah, so we assume polylog bits per entry. And we also assume that the solution has polynomial size in its coordinates, okay? And if you have, yeah, question? No, I just mean like, suppose that there is an optimal solution that satisfies this. Now put a box around your solution so that now it holds for all of them. So you can just require that, like, if you know that that the program has an optimal solution with a norm that's polynomially bounded, now you just put a constraint on each of your variables that they're polynomially bounded, and you don't change the optimal solution. But now you know that all feasible solutions are polynomially bounded in size. So it's very easy to enforce it. Yeah. Okay. So then we want to find an x hat, an approximate solution vector that's non-negative. The error in feasibility with respect to the linear constraint is polynomially bounded, and there's an additive error in the objective. And the reason we phrase it like this is twofold. So on the one hand, these are precisely what you get fast linear program solvers for structured problems for. Okay, so like that's for this notion of error, basically. And for these assumptions, so in particular, the polylog bits per entry is kind of the land in which the fast linear equation solvers live, and linear program solvers. And it also has the nice feature that when we think about whether there's a solver for, say, multi-commodity flow of this sort, if we assume such a solver, then we can map a solution back to a general LP solution. So we have like our reduction gadget, we also want to map back without incurring a large blow up in error relative to this notion of error. Okay, and the state of the art for solving linear programs, can I fix that somehow? Oh, the view. Maybe up in view? Up. Ah. Yeah. Okay, and I should not move around. So the state of the art is that you can do in terms of a number of non-zeros. So that's like not the only way you can frame this, but the state of the art is that you can do number of non-zeros, power matrix multiplication, or 2.056. So whichever one is larger. Okay. And so now, what about structured flow problems, structured linear programs? So here you have maximum flow. This you can do in what you hear number of edges is like number of non-zero entries of this linear program. And you can get a dependence that's 1.497, okay? And then, so then all of us people who make fast algorithms for flow problems, we were hoping to do the same for two commodity flow. And now I actually wrote down the definition. By this, I just mean you have two types of flow. Each of them must satisfy some demand. They must be non-negative, so that they're like live on directed edges. And they should not violate the capacity of the directed edge. Okay. So what's known here? Nothing, right? And so that's what we want to explain. Okay, and so the theorem that we show is that if we can solve two commodity flow in O tilde, so edges power some exponent time, then we can do the same for linear programs, with this being the number of non-zeros, and that's it. And the paper is here just because we didn't put it on archive yet. Okay, and this builds heavily on an existing paper from '78, which basically almost showed the same thing, except that he did this before it was known how to solve, like in fact in the same year that people figured out how to solve linear programs in polynomial time. So Itai was not interested in showing that like a tight relationship between two commodity flow and linear programs. He just wanted to show that if you can solve two commodity flow in polynomial time, then you can solve linear programming in polynomial time. And so because of this, the reduction has kind of some completely crazy steps that lose very large numbers, and you just don't want to do those steps. And it turns out if you just read it and you think a little bit longer, then you realize that it can be made very efficient so that it can prove this kind of relationship. So the reduction looks like this at a high level, right? So given an LP instance A with n non-zeros and some target error that we want, we'll produce in O tilde n time a two commodity flow instance B with the same number of non-zeros up to polylogs and a target error that's only polynomially worse, and will also give you a way to map back a solution to this B with that target error to a solution to this A with this target error and in the same time. Okay. So that's how the reduction works. And you can think of this as like soundness and completeness. Like one says we can express any linear program, and the other one says that if you have your solution, it's correct. And you should do some sanity checks here. So this is not really like a legitimate setup unless the new problem has not gone crazy in some way. And so one of the things you want to check is that it should have also a polylog number of bits per entry. Yeah. And so now I want to point out that I think we're actually getting at like a much more general phenomenon here. Namely that if you just plug in this idea, but with some you call it class X, then I think you should think of this phenomenon as class X of linear programs is sparse linear program complete. And I'm sure you can do a lot more of these, right? This is not so clear from reading our paper or Itai's that this might be a very general phenomenon, because the reductions are very ad hoc. But I'll show you at the very end, the last slide, that in fact there is like a very, very easy linear program that is sparse linear program complete. And so there should be a lot of other linear programs that can express that one. They're log capital N, but they're also actually, log of the norm of the matrix, you can think of it as. And so the only reason that that's okay is that we assumed polylog bits per entry, because that means that the norm of the matrix is polynomially bounded. Okay, so now we can rephrase our theorem as two-commodity flow is sparse linear equation complete. Okay, and now I just want to hammer on the restrictions, right? So we're working in fixed precision land. We can't actually show a relationship between these as like strongly polynomial-time questions, which would be another very interesting thing to do. And I think that you could generalize this to say, okay, what if I have some blow up in the size, here some parameter c, and then you should think of it as being sparse linear program complete with a sort of size exponent, this growth being c. And we always want, I think, polynomial error growth. Although actually, if you could make it constant error growth, you would start to prove something very interesting about kind of relationships between like crude approximation algorithms. So maybe you should also come up with PCPs in this land and like approximate reductions. So now I'll just show you what kind of at a very high level what Itai's reduction did, and then talk about how one should fix it. So Itai's reduction doesn't work when you have error, or rather he didn't analyze it. And also it wouldn't, because it's set up in a very kind of sensitive way, maybe. And then it blows up the number of non-zeros by a square. And it blows up the number of bits per entry from polylog, if you start with this, to O tilde n. So it's kind of, it has the right framework, but it's wrong in all the parameters, right? And only exact solutions, just to say that again. So what are his steps? So there's, I think, like just 7, 8 easy steps. I don't know if it's easy to put them all together, but that's what Itai did. So you start with linear programs. Then you reduce to, let's call them -1, 0, 1 linear programs, which is just linear programs where this constraint matrix only has entries -1, 0, and 1. Then you reduce from there to homologous flow. And then you have kind of a bunch of slightly wacky reductions between different flow problems. And at the end, you get out two-commodity maximum flow. So just in the interest of time, I'm only going to talk about this one, which is also where kind of one of the mistakes was, in some sense, one of the big inefficiencies. And you'll see it's very easy to get like an efficient one here. So what is homologous flow? You should think of it as a single commodity flow problem. So like maximum flow or almost, but with a couple of extra things that you can do. So in particular, you can take any set of edges and you can say these edges must all have the same amount of flow on them. Okay? And then you can take any vertices that normally would have some kind of demand on them and say, I don't care what the net flow is on that vertex. So the demands are only have to be kind of specified on a subset of the vertices, then they can be whatever you want on the rest. Okay. Yeah. You can, like, that second one is not very important. Like, you can very easily reduce that away. That's just kind of, I left it in there because it lets me very easily state the reduction from -101 to homologous flow. Okay, this reduction for Itai does this n-to-n squared size growth in the number of non-zeros. So that was kind of where that went wrong. So we want to make that order n. And then some step down here is which I hid, is what blows up the bit complexity. And this is really not something very fancy that's going on. Like, you just have to kind of define your linear program in a sensible way, as we did in the beginning, with like a constraint on the solution vector is not exponentially large. And then you have to track through all of your reductions that you're not violating this point. So we do that, and that controls the bit growth. Okay, so now let's see how homologous flow can express this a row constraint of the form -1, 0, or 1. Okay, so I have a row here which has plus x1 plus x2 minus x3 plus x7 equals 10. And I'm just going to make, for every variable, an unconstrained vertex, and then an edge, and then I send x1, x2, maybe I flip the sign here, x1, x2, and x7 into this vertex, and x3 out of it, and the net flow should be 10. And this quite clearly expresses that constraint up there. And now the only question for the audience is, why can I have a copy of x1 in every row where I need it? I have this homologous thing. It's kind of immediate, right? Like, I can just say all the x1 edges should be homologous. Okay. So where, that was kind of just a sample. There are like a few steps. You should not be super impressed with the proof. It should be the opposite. You should think we're soon in a world where sparse linear program completeness is as easy to do as NP completeness. And in particular, here together with Max Probst, who's my postdoc, and Ming and Zhang again, we show that this, so this is not online yet, but I guess will be before too long, that this linear program is sparse. Sorry, this should say linear program complete. So sparse linear program complete. And you only have two kinds of rows, right? Either you say that a variable is fixed at some, this C is unrelated to that. You just get to fix it to some number. Or you say that xi plus xj equals xk, right? So at least at the moment, this is sort of the closest that I can think of to something like 3-set is NP complete. And so now you can go home and you can find like other programs that are sparse linear program complete. And I can already tell you one example. For example, so there's a paper MN21. This will just be for the topologists in the audience. I don't know, do we have any? Maybe not. So topologists like to study what's called abstract simplicial complexes. And you can define flow problems on these And once you know that this thing is sparse linear program complete, then you immediately get that your higher order flow problems are sparse linear equation complete by a fairly easy reduction, except all of these things run into this thing that like we want an error analysis meta theorem, because like at the moment Ming is like the error analysis meta theorem. You know, I say like, let's prove that this is robust with respect to polynomially large errors. It seems like it has to be true. And then she sits for a while and proves it. But like, I think in general, there should just be a way to say like, if your reduction is reasonably well behaved, then that should be true. And so that's it. Thank you.